Okay, thank you very much for the kind introduction. So in this talk, I'm going to talk about quality, and not only in the sense of sensors, but also in the sense of software. So before we're going to start and getting actually into the subject, I've prepared a little example, which I unfortunately had to witness. And namely, it was somebody captured data at a construction site. The problem was he just purchased a laser scanner and didn't have any clue about what he was doing. The good news for him was, at least what he thought was, his friend was a construction manager. So he took his brand new laser scanner, went to construction site, captured the building shell before plastering. Then he had a look at the data, compared it to a construction standard, and found out that there are clear tolerance exceedances, which he then told Mr. E, his friend. And he was, as a construction manager, you're very pleased to hear these kind of examples. And he said, look, okay, I then go to the shell builder and I subtract 100,000 euros off his contract. Because if you get a wavy shell, it takes much more effort in terms of plastering, you need more material, it is more labor intensive, and hence the 100,000 euros that I take from you go to the plasterer. Problem for Mr. E was that the shell builder works consciously, and he had a legal protection insurance. So he sued Mr. E, saying everything I did was according to standards, and this has someone found himself in court. And this is essentially what we're going to talk about. How can we defend our generated results, which we generated with laser scanning, in court? The first subject we're going to have a look at is our laser scanner spec sheets, specification sheets, which are as given by the manufacturers. Then we'll have a look at transparency in the context of laser scanning software. The third question, of course, is can't we just simply cheat? And I'll try to answer the third point with a look at geodetic quality measures that we can also apply in laser scanning. And then I will finalize my talk with a summary and outlook. So the first idea, again, to defend yourself in court is to use a spec sheet, which is given to us by the manufacturers. So what do they tell us? They give us information about sensor accuracies, noise levels of individual sensor components that are built in certain instruments. I just took a total station or tachymeter as an example. And as you can see in the right-hand side, these are three different spec sheets by entirely different manufacturers. And you can see they all refer to certain ISO standards. So the good news, if you would have used a total station in these measurements, you could, as a start, you could tell, look, I'm using this instrument and the accuracies are reported to these standards. So you can see here the standard ISO 1700123 and different parts are actually regulating accuracy measures that can be found in these spec sheets. If we now look at laser scanning, the situation is slightly different. First of all, laser scanning is on the market for about 20 years. But still, they're also very different. So you can have laser scanners with very different specifications and capabilities. So again, I took the same question: can the provided information of a spec sheet help us in court? And then I had a look at 15 spec sheets of static laser scanners, which are the ones you put on a tripod. And I had a look at short, mid, and long range scanners. So short range scanners are instruments which have got a range up until, let's say, 100 meters. Mid range is 100 meters to several hundred meters, and then long range scanners is everything, up until several kilometers of reach. Furthermore, I had a look at 5 spec sheets of kinematic SLAM scanners, which are the ones which are carried through the object space. I will show you some images later on. And of course, I didn't name the names of the manufacturers because that could lead to legal trouble. I just wanted to show you how mad this entire laser scanning world is even after 20 years of commercial success. So the first thing that typically people look at is the rangefinder. So why is the rangefinder so important? The rangefinder is the key component of laser scanners. It is a reflectors rangefinder, which allows the laser scanner to capture unsignalized points in an object space. And it has always been the reference point of marketing. Our laser scanner is the fastest. It has got the most accurate rangefinder. The spot size is the smallest on market, and so on and so forth. But you need to know that compared to total stations, where you use a prism typically, so where you have a controlled optical path, unless of course you run the reflectorless mode, they're influencing factor onto the results. So the first one, I just mentioned 3 different categories. So first of all, we have the sensor domain. So we have different optical paths inside the instrument. Then we have the object domain. So the signal which has been emitted is then reflected by the object surface, and some stuff happens there. For instance, you have a different albedo value, a different quotient of reflection. The signal hits the object under a certain incidence angle. And of course, while the object travels through the atmosphere, there are dampening effects by the atmosphere. And of course, the range plays a crucial role in this. If you have a look at this subject in the realm of scientific publications, then you will find out that there are three key influencing factors which science had a look at. So one is the object distance, or the range between scanner and object. Then we have the radiometric properties, which is again the albedo, the surface properties, and we have the angle of incidence, which we're going to now have a look at what the manufacturers say in their spec sheets about these 3 aspects. So the first question, if I pose it as a question, is what precision can I expect at a certain distance E? So the first question that I had a look at was how many distance are specified for this scanner. So again, we have the laser scanner that you can see here on the left-hand side, mounted on a tripod, and we measure a distance E. Yeah, and we want to see, well, first of all, how many distance are specified. We can see here on the horizontal axis, we see the 15 spec sheets, and here on the vertical axis, we can see the number of ranges. We can see that 8 spec sheets specify exactly 1 distance. 6 spec sheets tell us 2 distances, and 1 spec sheet tells us a lot compared to the others, namely 5 distances. Now, what is not interesting is how many there are. Of course, it is also important, but the interesting thing here is which ones were specified. Because what is interesting, if you read these spec sheets, is that you always find information about what's the longest range of a certain laser scanner, but not what the accuracy, which accuracy could be expected at a certain range. So what I did was I had a look at the longest range which was specified, where I had a specific noise level or an accuracy measurement, and I set that into relation between the maximum reach, because that value was always smaller than the longest specified distance. So, and then you can see something very shocking, in my opinion. Namely, you can see the best, in air quotes, value you could find was here, roughly crossing the 50%. So that means if you would purchase a scanner which has got a range of 300 meters, you would get at best a noise level, or a value of a noise level at, let's say, 150, 160 meters. And what is even more shocking is you can see that a lot of manufacturers only give you values which are very close to the scanner. So about 10% of the maximum reach. And again, this is shocking from an engineering perspective. It would be as if you would purchase a car and you'd be interested how much fuel or energy it takes at 120 kilometers per hour, but you would only find values at 20 kilometers per hour, which of course would look very nice, but are not very realistic. So the findings of the small experiment, the specifications tend to be closer to the scanner. None of the manufacturers goes even close to the maximum reach. And you couldn't see any significant differences in the specifications between short, mid, and long range scanners. So again, it's an entire mix. So let's look at the third very interesting category, namely, the second. What precision can be expected on different surfaces? So now I had to look at different materials or at different albedo values that the manufacturers specify for the scanners. That's the first question. And the second one is, which albedo levels are reported? So, and here you can see, again, the 15 on the horizontal axis, again, the 15 spec sheets for static laser scanners. On the vertical axis, you can see this is the albedo, or the quotient of reflection. And you can see that 7 spec sheets don't tell anything about these values. You can see that 4 manufacturers specified, which I think is very good. You see here there's a high albedo, which refers to something to a material which reflects a lot, or quite good. Something in the mid, and something not as strong in terms of signal strength. You can also see here some manufacturers even go a bit below that, which is fine. As a user, you'd be interested to see a hard variety of that. What is a bit, yeah, I don't want to use the word shocking too much, but you can see here that in these spec sheets, there is only values given for the strong, for very bright in the optical sense materials. And you can see here, this is just an example of a material. This is white silicate plaster, which has got an albedo of 79%. And you can see here the manufacturers, or 3 spec sheets, are pretty close to 80%, and that one even crosses 80%. Just to give an idea, in the visual spectrum, fresh snow has got an albedo between 80 and 90%. So not very realistic from my opinion. So the question, what are my findings? So do the manufacturers like to answer the first question? 7 spec sheets don't tell anything, so preferably there's no information given at all. Question number 2, some spec sheets refer to highly reflective surfaces, which is again not very telling. If you then like to know which level of accuracy can I expect on the construction side, as an example. So the key findings of part 1 are, as a practitioner, you should actually never scan further than the distances for which I have a noise level specified. Never scan on darker surfaces than specified, and then never scan at different angles of incidence. So never different than 90 degrees. We know, or science knows, that the angle of incidence is quite critical, yet it is not specified at all. So if we summarize this, spec sheets don't tell us anything, which is, well, actually very sad news. So the question is, what can we do? So now a look at an experiment that we conducted a couple of years ago. So what we did was we took a laser scanner, as you can see here on the right-hand side at the very top. We performed 1D measurements, which you typically cannot do with all laser scanners. But with this laser scanner that we used, we were able, just as a total station, to measure repeated distances. So we repeated 1 million distances, and then we computed the standard deviation and the raw intensity values. And then we did this for, I think, 80 different settings, different ranges, different incidence angles, different materials. And then we plotted it here. So you can see every dot that you see here in these 3 graphs is on the horizontal axis. You see the raw intensity values, which is the signal strength that a laser scanner reports apart from just coordinates. And we see here the standard deviation of ranges on the vertical axis. And what is noteworthy to point out is that you can see here, we see a certain characteristic. You can see here in the first picture, you can see different measurement rates, which don't make too much sense for you now, but every one of these different lines follows a certain characteristic. So that was just these black dots as an example, follow this differences in distances. Then we can see here, we took more samples under different angles of incidence. You can see here ranging from 16 to 63 degrees. So that sample here at the very top, that one has been tilted. We had a look at the standard deviation, and we found out, okay, it also follows this trend. And then we used different samples, which we've seen on the 2 slides before, the white silica plaster, for instance, and then they also follow this characteristic. So what does it tell us? So first of all, we could use another representation of accuracy than just discrete values. So what we've done here, we used the precision. What we actually showed here is that the precision is dependent on the signal strength. So if we use raw intensity values, we get this kind of curve. So the basic idea is that instead of using discrete values, which are incomparable, as we've seen, and replace this by a steady function. Now, the question that I'd like to answer now is, we've seen that regardless if we change the distance, the angle of incidence, or the materials, it always followed this trend. So why does it actually consider, why do raw intensities actually consider the noise level? So the answer is actually quite simple. Namely, this is the LiDAR range equation. And just in brief, all these different domains, sensor domain, object domain, and environment and atmosphere, are actually considered on the right-hand side of this equation. So you can see here there's an atmospheric component, there's a system component, we have range in it, we have alpha is the angle of incidence, we have the wavelength of the scanner, we have the aperture diameter, and of course the strength of the emitted signal. And that can be used to compute PR, which is the power of the received signal. This is what the laser scanner receives, and which is then used to compute range and of course intensities. So, and this is all inherently given in this beautiful piece of math. So what can we do with it? So essentially what you could do on the left-hand side, you can see, if you've ever been to Berlin, this is a graffiti on the wall of Berlin. And this is the intensity level. So it's actually looks like a grayscale image. And for every one of these pixels, you can get an intensity level. And you can see again, this is the trend that we used. And if you approximate a steady function through this, then we can simply take an intensity value, have a look at which intensity level, which range noise I can expect, and then I can use this information, use variance, covariance propagation, and marry this with the angular accuracies, and then I can compute 3D accuracy levels for every single point, yeah, which is much more meaningful than just and I can do that for every single point, which has to be mentioned here. All right, so, but the bad news is there is something missing, namely, just having sensor accuracies doesn't help you in practice. It's because it's just one component of a bigger piece. If you like to capture data with a terrestrial laser scanner or static laser scanner, you can see, let's say we want to capture this object, and I've captured data from this viewpoint with my laser scanner. I put it on a tripod, I perform the scan, and all I see is this. So I only see the front side of it. So if I want to capture the object entirely, then I need to change my perspective. And then, of course, I have scans from different perspectives, which I then have to merge or marry or register, as it's called. And so there is another component to it, namely a mathematical component, which, just like a puzzle, assembles different pieces, different scans to one common data set. If we use a kinematic laser scanning system, then I don't use a tripod. I simply carry it around the object space so he can see a trajectory. So I'm moving the sensor through the object space. I don't have the necessity to register the data set, because that is inherently been done by this sensor. So let's have a look at these kinematic scanners first, and then we move on to how we can compute or how we can express quality in the realm of software. So until now, we talked a lot about sensor accuracy. So here, what is interesting, I had a look at 5 different scanners, and all mention the same central accuracies, namely 3 centimeter, which is copied from the manufacturer of the laser scanner, which is used in these kinematic systems. What is interesting here is the algorithmic component, which some manufacturers specify to 1 to 5 centimeters. And here it is interesting to point out that this is the accuracy of the rangefinder, which is the key component. And 3 manufacturers say that the overall accuracy is much smaller, which is, again, fishy at best. So the second part of this conclusion, which was very short, is some algorithmic quality measures are given in the data sheet. The problem is, just in accordance to static laser scans, I have no clue what kind of scenario, what kind of survey configuration they are referring to. So, and the problem here in practice is that there are no reliable quality measures from SLAM optimization. Typically, you're given values, which we'll have a look later on, but we have no clue where they're coming from. So, just to summarize this very short part on kinematic laser scanning, so these data sheets don't tell us anything either. So the question is, how can I report quality which I have achieved based on point clouds, for instance? So, and that brings us to the first problem in data processing. The problem in assigning quality to point clouds is actually a tricky one, because let's say we want to capture this data set again, and now I've simulated different point clouds which have been captured from different viewpoints. So I just take a look at one profile, and it should be mentioned that all points which are simulated are error-free, which is something that, of course, would never happen for real-world scanners. but just to give you an idea what happens, it is easier if you do that with error-free values. So you can see this is the profile, which then samples an object or one slice of the object, and then I'll slightly change the position of my virtual scanner, and you can see that the point distribution is slightly different. And then do it again, and you can see that I have 3 different representations, which all depend on from where I've captured the data and how the scanner coordinate system was oriented. So what do we see? So actually we can tell that laser scanning is a polymorphic measurement method. So that means even though I have error-free measurements, if I connect these 3 different data sets, you can see there are large discrepancies just because the points are differently sampled in the object space. And this is essentially one of the biggest problems in processing laser scanning measurements. So what we're going to have a look at in the next part is we're going to have a look at 3 different strategies for quality assurance in static and kinematic laser scanning, which are look at contradictions between point clouds. We're going to have a look at contradictions between orientation parameters, and we're going to have a look at contradiction to control points. So these are 3 very different strategies how to express quality in point clouds. So a small example, because if you've ever dealt with laser scanning data before, you've probably seen funny effects. And I just like to, if you've never witnessed this, I'd just like to show you this on a very stupid example. So you should know this gentleman here on the left. We've already seen the lady on the right. And if I would take these 2 data sets, I would register them together, which doesn't make any sense from the data perspective. But it is interesting to point out, to visualize some effects. So what do we get afterwards? We get 2 interesting findings. We get very good numbers, as you can see here, 0.59 millimeters, which if you would just look at the number and you wouldn't know what the data was, you would say, oh, that's great. Good news. This is a very good example, very good data. But then you would look at the outcome and you would be utterly confused, in my opinion, because of course the input data did make sense, but how come the numbers are great and the outcome is rubbish? So, and this can be explained how these metrics are computed. And this is what we're going to have a look at now. So in all examples in the following, we have the following input. We have a gray surface, which we digitize with 2 point clouds. We see an orange point cloud, and we see a green point cloud. And now the question is, what's the quality of this relative orientation between the green and the orange data set? The first strategy that we can use are so-called point-to-point correspondences. So that means I'm trying to find, let's say I'm starting at the first green point. I'm looking at what is the closest point to the closest orange point to the closest green point. So, and if it's this one, then I'm drawing point-to-point correspondences. I do the same for the next, and the next one. And then I'm computing the length of the vector between these corresponding points. Now it's getting interesting because the metric that may be reported is not typically, are not typically all points in the overlapping region, but just a sample, typically 0.1% to 1% of the entire overlapping region. So let's say if I have 10 million points in the overlapping region between 2 scans, I'm not using all of these points because it is way too tedious. The runtime is taking too long, and of course it needs RAM to be computed. And then the next interesting bit is that the metric can be the mean value, could be the median, or it could be an entirely different number, which you have to be watch out what it really is. So the verdict, the advantage is it can be rapidly computed. Disadvantage, it is sensitive to differences in local resolution. So if my points of the orange data set would be very coarsely sampled, I would get very large residuals just because the point distribution is different. So a strategy that can cope with differences in local resolution is point to triangle correspondences. What I'm doing here is I'm taking my reference data set and I'm triangulating this. So you can see these gray bits. This is triangulation through the orange data set. And now instead of saying this green point belongs to this orange point, I'm taking the green point and I'm trying to project it onto the gray triangulated surface. If it is possible, then I'm computing the length of the vector between the green point and the perpendicular foot point, and you can see that it is already smaller than a point-to-point correspondences. Again, I'm computing these metrics only for a subsample of the overlapping region, and the metric can be the mean value, median, or something else. That's identical. And the verdict is, again, the good news is that we can compensate for differences in local resolution. The bad news is there are ambiguities. So because a point may fit to several triangles. Let's say I have a point that is located here, and it can be projected to this triangle or to that one. Do I pick the long one? Do I take the short one? Which one? So which point does this, to which surface does this point belong? That is not entirely clear. So let's have a look at an example. In this case, I computed the mean value of the residuals. For point to point, I receive a metric of 7.8 millimeters. And just a small reminder, the geometrical input is the same for the two strategies that I showed you. And now this is a bit disturbing if you've never witnessed this, but if I now compute the same value based on point to triangle correspondences, I get a value of 3.4 millimeters versus 7.8 millimeters, even though in a geometrical sense, the outcome is identical. I just use a different metric. And this is, again, can be quite disturbing if I get a twice as accurate result in terms of numerical values, but all it is are just different metrics. Let's have a look at another, at the reason why the example that I showed you with the Gauss bust and the Nefertiti bust, which have been apparently nicely registered, even though they weren't, how this happened. So what I did was I took the green example from the previous example and I falsified it I rotated it by, I think, 20 degrees, as you can see. So they actually don't fit at all anymore. So, and then I'd like to show you a adjustable threshold, which can be found in most software. Sometimes it's called maximum search distance, sometimes it's called correspondence threshold, and sometimes it's called tolerance. So what this value does is it generates correspondences based on point to point or based on point to triangle. And if the length of a residual is larger than a threshold, it simply cuts it. So in this case, you can see here, this would be now, it's now tinted in red. So that means it is larger than a predefined threshold of 3 millimeters. And even though that this data set is not correct in terms of alignment, again, I falsified it, the numbers make us believe that it's good. So you can see 2.7 millimeters, 7.5 millimeters, 2.5 millimeters, because you simply cut out the values which you dislike. Yeah? So, and this is the reason why we've seen this effect earlier in this presentation. So, what the contradiction between point clouds tell us? So first of all, the meaning, if I would have to define a meaning behind this, I could say that the selected points in the overlapping area of points deviate from each other by X millimeters on average per median per whatever the metric, is used. It is not meaningful if the following is unclear, because you can compute these numbers based on the block adjustment when you have more than 2 scans. So let's say 1,000, and there's a certain overlapping region where, let's say, one region has been captured by 5 scans, or it can be computed based on 2 scans, as we've seen before. Then it is unclear which points were used. Have I taken every 10th point? Have I started counting on, just as an example, have I started computing, taking the point from the left? Have I started from the right? Which strategy was used? Was it point to point? Was it point to triangle? Has a correspondence threshold been used to polish the result? And how was the quality measure computed? Was it the median? Was it the mean value? Were it the best 18.37%? That is typically really hard to find out and not always documented. What do we need? As a precondition, we always need an overlap between different scans. You can see the list of disadvantages is quite long, and this is why it is not really understandable why this is still the standard quality measure in most commercial software and in science. And this is, again, disturbing to say the least. So are there better or different ways how to compute it? Yes, there are. And instead of using the point cloud as an input, we use the orientation parameters as an input. That could be, for instance, registration parameters, or it could be kinematic parameters. So, and instead of now looking at the point cloud, we just look at the input parameters. And then we use mathematical constraints. The first constraint that you probably learned was in primary school. If you have a planar triangle and you measure the inner angles in that triangle, you know if you sum them up, they should add up to 180 degrees. For the surveys among you, if I do leveling and I sum up the back and forth sides, I should receive a value of 0 millimeters, namely no contradiction. Typically, the latter is not the case. So typically, what you want to have is that the contradiction is roughly as large as the predicated accuracy, then everything is fine. But if the contradiction is notably larger than the predicated accuracy, then we know that the data contains error. And this is the general idea behind this. So what we do is that instead of using height difference or angles, we use transformation parameter sets or kinematic parameter sets. So that means we have six dimensions. We have 3 translations, 3 shifts, so to speak, and 3 rotations. And what we want to have is just an example of a small triangle here. So let's say we have 1, 2, 3 stations that are connected by 3 different sets of registration parameters. We'll start registering here, go here, then to the third station and back. Then I should I should receive a so-called 0 transformation. That means that first of all, that the position and orientation are verified. And just to give you a more visual idea of it, or how you can think of it is, let's say we start at the green scan. We create a virtual copy of the very first scan. We then register to the blue scan, to the red and back. And we don't take the original scan, but the copy. And then in the end, the orientation and the position of the green scans should be identical. This is the general idea. If this is not the case, you can see that here there are differences in orientation, and there's a large offset. Then we know that something is funny. Yeah. So again, this actually the good news about this strategy is that it is not. You can find a lot smaller contradictions compared to point cloud strategies, and of course, it is not as error prone as we've seen. So the conclusions, the meaning behind this strategy is that the transformation parameters between scans or kinematic segments differ by x millimeters or y degrees. It is not meaningful when 2 or more parameter sets fall into a false solution. This effect is very unlikely, but still I want to mention for the sake of completeness. What we need is, or what the precondition of this is, that we need a redundant set of transformation parameters. We'll get to talk about this in a minute later, but a redundant set means that you have closed loops. So again, the example of 3 scans, if I have 3 scans and I only have 2 sets of registrations, that is uncontrolled. I have no redundancy. If I have a third set of registrations, then I have a redundant set and I can control and verify the accuracy. The good news about this is that you can verify each and every individual degree of freedom, namely all shifts and all rotations. And then you can see on the right-hand side, this is how it could look like. You can tell for every scan, the color of these arrows indicates the contradiction between the registration parameters. So, and now let's come to the gold standard in quality assurance and laser scanning, which are artificial targets. Artificial targets are still used, despite the fact that of course, it takes manual effort to bring them into object space, but still they are used a lot because they are considered to be unbetrayable in practice for quality assurance. You can use them in 2 different ways. First of all, you can use them in a local fashion, so you can you can use these different targets. You can bring them into the object space. And then you can use them to register different individual scans. But we want to use them in a different fashion. Namely, we want to use a total station. We survey, this is a sphere, for instance, we survey the center of the target. And then we're going to use that as a ground control point in the following. Then we capture the same sphere with a laser scanner. So we have a local coordinate. And then we generate a so-called point identity between the superior coordinate and the local coordinate. So, and again, this is to consider the gold standard. So what we're going to do is we're going to have a look at an example, which is a construction site in an industrial plant. You can see on the bottom, this is roughly how it looked like. Stainless steel. about 370 static scans. We have 200 by 150 meters of surface that was captured. All scans are connected just like a puzzle by 584 pairwise registrations. We have 63 ground control points, and we have 327 connections to the total station network. So, and the accuracy requirement in this example was 10 millimeters. And in the following, I'm going to show you because an example for self-deception, because I asked the question at the very beginning, can't we just simply cheat? And now I'm showing you strategies how to cheat and how you could verify or how you could prove that you haven't cheated. So this is what we're going to do now. So the easiest way how to cheat is you delete unwanted point identities. So if the discrepancy between a local point and a global point is too far for your lightning, then you just simply say, tell your trainee, look, delete everything that is larger than 10 millimeters in this example. So we can see here, again, this is the network. We can see the triangles. These are my ground control points, and every triangle that is red has been deleted. So you can see that I only use, as an example, only a very small portion where I would get great numbers. But again, I would only use a very small portion of the original ground control points. What the influence is, I will show you in a minute. Second way how to betray would be cutting up the project. So you don't delete points, but you cut the project into pieces. So you can see here, again, here by the scissors, I cut the project here, I cut it here, and I have 3 targets, for instance, in a small sector. So it would still be enough to reference this sector. But the downside is that we'll get, how should I say, that transition areas which are unclean. So for instance, here, everywhere I've cut the network, I will get imperfections. So let's say I have something like this, I will get a shift, for instance, in here. So again, these are the 2 solutions. I could delete control points, or I could split it, the project into individual blocks, so that every individual block is still connected or attached to the total station measurements. So what are countermeasures to do this? So the classic, what people like to report is they just say, look, I have ground control points. I have, let's say, 3.3 millimeters on mean. I have a median of 2.7 and max 7.7 millimeters. And thank you very much. That's it. So the problem is that not all scans are surveyed. So if, let's say you can see this is a part of the network, and I can use geodetic quality measures to verify or to identify weak scans in my network. So what you can see here in this magnified area, you can see the colors. You can see green here. We can see everyone. So this is a scan. This is the next scan, and you can see that these scans are connected by different registrations. So the controlledness of this network, of this local part of the network, is good. But here we have what I refer to as a toilet scan. I have the toilet. I open up the door. I take the scanner in. I do 1 registration, and then I go out. If this registration is wrong, I have no possibility of telling that this is correct or not based on numbers. So that's impossible. So what I would then have to do, if I would have to verify this this network, the only way I could prove the quality is I would have to have a look at the point cloud and have a visual inspection of it. That would be the option which I dislike the most. What I could do instead is I could either add more registrations if possible. For instance, from here, add another registration to another scan, or add another ground control point if it is really needed into this room. So just to summarize this part, so partial redundancy measures, which are visualized here, can help you to identify how well controlled my network is. And if you have no redundancy, you have no clue, no idea how good your outcome is. So what else can we use from our toolbox in geodesy? The problem of using residuals is that they're datum independent, which means regardless where they are, the numbers will always be the same, which is good in some degree. But if we go back to the example where I simply delete point identities, I would expect to see something funny, but you wouldn't. You would not see anything if you just look at the residuals. So, and what you can do instead is you can perform error propagation and compute the so-called stationing error. So that translates to how my scans wobble in relation to control points, for instance. Here, just an example, we have a line of jigsaw puzzles and that are connected, and what everybody reports are relative accuracy measures from scan to scan, from scan to control points, for instance. But what these measures don't tell you is how they accumulate. So if I just imagine I have hold my thumb, this is my control point here, and then I go to the end of the puzzle and I start wiggling. This is the absolute accuracy values that I'm interested in. So namely, how stable is my network with respect to my control points or my reference. So, and yeah, what I can do based on error propagation, I can compute the so-called stationing error. And we can see here, these are the locations where my control points were. So here you can see the small triangles. These are my control points. And then you can see the colors of the stations. Yeah, so everywhere where you get control points, it looks kind of greenish. And the further you go away from it, you get this extrapolation. And then you can see that it turns red, and we exceed, I think it's more than 3 centimeters at max. Yeah, and this is something you would expect because it's very similar to mechanics. If you delete everything and narrow it down to a very small area, it wiggles a lot. And it's the same that we can use in these with these quality measure. So the good news is we can use geodetic metrics to verify that we haven't cheated. But there is more. So this is the last example that I will use. And I've seen this during the presentation of a sales representative. He sold kinematic laser scanners, and he used a dodgy example, which I like to, which is good for teaching, but it's, again, dodgy, and you should not use it. So what he did was he used a kinematic laser scan. He used 10 ground control points that he observed with GPS. And then he showed the residuals between kinematic scan and the ground control points, and all residuals were in the sub-millimeter range, which was very disturbing. So, and just to give you an idea, so let's say the banana is my kinematic laser scan, could also be a static laser scan. So if you're offended by the example, then we have used local targets that are in the object space. They have been captured by the kinematic scanner. And then the GPS points were associated to it so that they form point identities. And then, again, the residuals were all in the sub-millimeter range. And how is this possible? How did that happen? So the results like this can be achieved by inadequate weighting. So now the question is, how can we do this? So, and just an example, and it is heavily related or correlated to the question of what is an outlier. So let's say I have a chassis of a car, you can see on the right-hand side, and I use 3 different measurement devices to measure its length. So, and I do that 10 times, and then I compute the standard deviation. I use a laser tracker, which is industrial type measurement device. I have a total station, and I use a Swedish furniture house paper tape measure, and I measure that again. So the accuracy, which I assume for the tape measure is 2 millimeters, for the total station 1 mil, and for the laser tracker 5 millimeters. Again, I do measure the chassis 10 times, I compute the standard deviation, and the outcome is 3 times the same, namely 1 millimeter. That, of course, is just an example, but it shows you how weird the world sometimes is. Namely, the question is, what is now a good outcome? What's a bad outcome? And how can I numerically prove that this is the case? So what I do now is I use, again, another tool from geodesy, namely normalized residuals, and which is, if you come from other fields of engineering, it is very similar to the signal to noise ratio. So again, this is the classical notation, signal to noise, or in other words, I take the residual and divide it by the accuracy. If I go back to my examples, this is the outcome of my tape measure. I simply say I have a standard deviation of 1 millimeter. I assumed it to be 2 millimeters. So the ratio is 0.5, which is a triumph because I've performed better than I expected. If I assumed 1 millimeter and received 1 millimeter, you can see the ratio is 1. So I actually confirmed my expected accuracy. And this is what you always like to see in surveying. You want to prove that your assumed accuracies are the ones that you receive. This is, again, what every surveyor dreams of. And this is a catastrophe because you can see the ratio between 1 millimeter and 5 micrometer is 200. So we have performed 200 times worse than expected. And again, this is a catastrophe. So just as a small rule of thumb, which is the called 3 sigma rule. If the signal to noise ratio is larger than 3, then the observation is probably an outlier. Yeah, so in this case, clearly an outlier. Something must have been wrong. In the two other cases, everything was fine. So let's go back to the example of our kinematic laser scan. So what are the consequences if you use inadequate weights? What would happen if you, for instance, have GPS values and you say they have sub-millimeter accuracy? You deform or distort the inner geometry of the point cloud. So I chose the banana for this for the sake. You have a curved banana, and if you put too much tension on it by using inadequate weights, you bend it straight. So this is definitely not what you're looking for. So the question, weighting is one thing, but whether it's plausible or not is actually entirely different kettle of fish. So what we're always interested, we like to prove that my weights have been plausible. And again, here, this is the example which I tried to replicate. I used GPS points and I falsely weighted them, and then you can see the assumption versus reality has performed or has yielded in a factor of 10.71. So I've performed 10 times 7 worse than expected. And this is something which you cannot show by just looking at the residuals. So that was it from my side. So just to summarize, for laser scanning hardware, even though laser scanning is more than 20 years old, it's still a Wild West. So marketing has actually created some kind of a parallel universe to classical other surveying instruments. So that means that if you're as a user of laser scanners, the spec sheets are still incomparable. Every manufacturer refers to different scenarios, different ranges, different albedos, and hence you as a practitioner can hardly use the information at all. But there is hope, as I showed you, that current research tries to focus on quality assurance of point clouds. So which is definitely good news. If we look at the laser scanning software, it's the same. Namely, it's also the Wild West because the metrics are poorly documented or not even documented at all. So you get numbers, but you don't know what they're based on. We know, and I've showed you, that the survey configuration has a significant impact on the outcome. The problem is that most software is not able to assess the network's stability. Namely, all the geodetic metrics I've showed you can be typically not found in these in most commercial solutions, and hence the dirty tricks that I showed you will work in these softwares. So if you delete, if you cut, if you betray, you will not be able to tell if somebody tried to cheat. So, and the flip side again, very few software compute meaningful and sound quality measures. And that also means that legally secure software with transparent computations are very rare. And this is actually very bad news if you get into this industry. So that was it from my side. Yeah, thank you very much for your attention, and I'm looking forward to your questions.